Well, good morning, afternoon, evening, wherever you are on this globe, and welcome everybody to our second series of oil and gas related webinars. Today we will have Robert Huth, and in the background Benjamin Lucas, the training manager from our production center for temperature in Germany, to talk on the topic of temperature measurement in cryogenic applications like LNG, for instance. Robert is our senior product manager for temperature. He's also the leader for one of the strategic directions for the global oil and gas industry development group within Endress Hauser. This webinar will last roughly about 45 minutes, 30 minutes presentation, and 10-15 minutes questions and answers. Just put them in the questions section of your GoToWebinar on the right-hand side of your screen. My name is Rob Vermeulen, and I'm the Global Industry Manager for Oil and Gas at Endress Hauser, located in Greenwood, close to Indianapolis, Indiana, in the United States of America. Before we start, we'd like to have a safety moment, as is a custom at Endress Hauser and in the oil and gas industry. I like to focus on the corona crisis. Please wash your hands on a regular basis and keep at least 6 feet or 1.5 meters distance from each other. Wear a mask when in public, avoid coughing in public, and use a national tracking app when available, please, because that helps. So, Endress Hauser, just a small introduction. Endress Hauser is a global company employing over 14,000 people worldwide and has a revenue of 2.6 billion euro. Our headquarters is located in Basel, Switzerland, and our core business is to develop, produce, and service process and laboratory instrumentation to measure quality and quantity parameters. We own and license over 8,000 patents. And with this, I'd like to hand over to Robert so he can introduce himself and the topic he's going to talk about. Robert, I see a beautiful scenery behind you. Where are you located, man?
Yeah, welcome, Rob. Thank you for the introduction. Welcome, ladies and gentlemen. Good morning, good afternoon, wherever you are. Welcome to our session today. It's about temperature solutions in cryogenic applications. So we are located in Nesselwang. It's in the south of Germany, and it's the headquarters of the Endress Hauser Temperature and System Products division. Today with me is Benjamin Lucas. He's our technic boss today, and he will also take care for your questions collected, and I will try to answer them after the presentation. So please do not hesitate to ask any questions at any time.
And yeah, warm welcome also from my side. And for all of you, this is a little bit different maybe from other sessions or other webinars you experienced lately. And we want to interact with you a little more, so to really get your feedback right here with us in the video studio. So therefore, please take a screenshot from that QR code, or if you don't have a mobile at hand, just go on www.menti.com and enter the code 3603173. And you are right directly in our interactive polls. And we want to have your feedback throughout the session. And if you join there, then we will be able to also see that here on screen live. There is no installation, no app download, no tracking. So everything's secure from your side, but it's more fun for you and more fun for us, and especially for you, Robert. So therefore, please join us here. And I give it back to you for the important part. The knowledge part, the information, the presentation. Thanks.
Okay, thank you, Ben. So, as we see, not too much people answered by now, but every time when we have a question, we will again then also give you the code and the website that you can use. Okay, so let's start. Some points about the background. So, whenever there's trade, of course, there's measurement involved to quantify the goods that are transferred. And whenever there's measurement, of course, there are also errors and uncertainties behind that. So there's a LNG projects group that try to improve and develop methodology for LNG with the aim to reduce the measurement uncertainties and the reduction of financial risks. In the end, make trade of LNG more transparent. These projects are a joint research group carried out as part of the European Metrology Research Program, and it's supported by the European Union and also by the countries and the European Association of National Metrology Institutes. Under the frame of these projects in Rotterdam harbor, there has been built a liquefied natural gas research and calibration facility. This is the first site that will be able to calibrate and test flow meters, analyzers, sampling systems, and other LNG equipment utilizing LNG as the liquid during the test. So quite a good and important project. So if we are now talking about this project, this calibration facility has been built by VSL. It's the Dutch National Metrology Institute and an internationally knowledge institute in the field of metrology. The institute has built the most accurate calibration plant for flow meters operating in LNG in the world. And Endress Hauser has been asked or has gotten the possibility to install our temperature sensors there. These temperature sensors have been developed together with VSL, so especially for this project, for this application, and have also been qualified and tested inside of this plant. This facility will be accessible for customers to calibrate flow meters, test sampling systems, and calibrate gas chromatographs. Also, temperature sensors might be calibrated and tested in there. So what are the requirements for temperature measurement in LNG? So accuracy better than plus minus 0.5 Kelvin at minus 160 degree. Process pressure 10 bar, a fluid velocity of 8 meters per second, medium temperature minus 169 because the complete plant was qualified and also calibrated with liquid nitrogen. And the ambient temperature minus 100 up to 50 degree, and the complete assembly is an ATEX XI area. So from the beginning, that doesn't look too critical for temperature measurement. But what do you think? What are the major difficulties for temperature measurement in LNG applications? So please use Menti, type in some words. What do you think is the major difficulties for temperature measurement in LNG? Any idea?
We need you again. No time to watch YouTube videos. Right here is the place to be. And we get the first result. So Robert, you can quite directly tell us something about what you think about it.
Yeah, okay. We see accuracy here. Yes, definitely. We'll come to that point later. Ambient error as well. Temperature range. Yes, of course. Stress, I think it's thermal and it's mechanical stress. Absolutely true. Cracking. I'm not sure if that's the mechanical stress. Not sure about that. Stratification. I don't know what that means. I'm sorry. Mechanical loads, yes. Insulation, absolutely. Okay, then I think we have all that. Most of them are right. Absolutely. So let's have a deeper look at the requirements. So we said accuracy better than plus minus 0.5 Kelvin. What do we have to think about? So it's at the first step, it's the accuracy of the sensor element itself. Then it should be an exchangeable sensor for recalibration to see if it's still okay. If we want to have a high accuracy, of course, we should think about digital communication. And for this high accuracy, we should also think about sensor transmitter matching. So modifying the transmitter in a way that optimum result comes out of the sensor. 10 bar process pressure and a flow velocity of 8 meters per second. Of course, for these conditions, we have to think about the stability against flow-induced vibrations. And with a temperature range from minus 169 to plus 50 in the ambient, of course, we have also to think about heat distribution, heat transfer, and also thermal shrinking effects. So how do we do that? So, of course, with these points, we started the development together with the colleagues in VSL. If you think about the sensor element, so the selection of the primary sensor, we could think about thermocouple, but at this minus 160 degree, they have a very low voltage and a low gradient, so it's hard to measure or to transfer the right temperature. Then thermocouple have a low accuracy, so minimum plus minus 1 Kelvin, and that's only valid for new thermocouple. And also a bad effect, thermocouples, you are not really able to calibrate thermocouples and to check if they are okay or not. So that doesn't work. And sensor transmitter matching is also not possible with thermocouple. Then if you think about the standard RTDs, according to the IEC, for this temperature range at minus 160 degree, only class B is available. Class B in this temperature range means an accuracy of plus minus 1.1 Kelvin. And if we also think about the ambient temperature and the heat transfer, the complete sensor would not be accurate enough. So our solution was a special PT1000 element. It was qualified for the low temperatures. We have a special temperature, thermal characteristics of this sensor, and we had to put this special characteristic into one of our transmitters. The TMT162 is able to work with individual characteristics of the sensors, and with this solution we were able to achieve the highest accuracy for the minus 160 degree. Well, the second challenge is the temperature transfer and distribution. So every contact thermometer is only able to measure its own temperature, so the temperature of the sensor element, like the PT100 or here the PT1000. So knowing this, we have to develop a thermometer that is able to transfer the heat, so from the process medium through the thermowell to this sensor element. Of course, if the temperature sensor is able to transfer heat, it's also influenced by the ambient temperatures. So with the standard sensor, like we saw it in some pictures ago, what do you think? Which is the estimated or the possible deviation caused by heat transfer in this temperature range? So between minus 160 and 20 degree ambient temperature, what do you think is the failure that we get purely by heat transfer in this temperature sensor? You have here a range, it's from about 1K up to 10K. So what do you think is the failure that we get in there? Okay, we've got 3 answers, maybe. Are there some more people that want to answer? At the moment, we are at 4.7 degree failure. Some of you think it's quite small, so about 2 Kelvin, and the other think it's between 5 and 7 Kelvin, maybe. Okay, 4.3 Kelvin. Not too bad, this estimation. We made some calculations, some simulations, and also some tests. And we came up with a deviation of about 5 to 7 Kelvin in the end for a standard sensor. So why is that? If you now look to a standard temperature assembly like this one, we have a head, we've got the neck tube, we've got a process connection here, a flange, and a bar stock thermowell. So we've got 2 different temperatures. We have the ambient temperature, which is in our case higher than the process temperature at the tip of the thermowell. And we will get this temperature distribution. So we have a gradient inside of the thermowell stem, and depending on where the sensor is located, we either are able to measure the process temperature or we already measure a higher temperature. So the sensor element has to be placed as deeply inside of the thermowell as possible. And then we've got heat conduction in the material of the thermowell and of the neck. And outside we've got some convection if we do not have an isolation, and all these factors have influence on the temperature that we are measuring. So inside of the thermometer, we've got an energy transport. If here the temperature is higher, of course the transport is into this direction, and this is also leading to a temperature balance from the outside to the inside. So we are also able to heat the LNG inside the process if we have high temperatures outside. So how are we able to solve this issue? So the solution for the temperature distribution is a long and thin thermovalent sensor. So this is the thermal well we have. It's about 50 millimeters long, and the insertion part of the thermal well is only this 50 millimeters. And we also use a very, very thin, so a 3 millimeter insert for our measurement. So you don't really see it. Here, can you see it now? No, it doesn't work. It's too thin, sorry. So the ratio length to insertion is about 10:1, and the length to diameter ratio is 25:1. So with this long length, we have the possibility to reduce the heat transfer from the outside to the inside. Next step is the vacuum isolation. So the sensor, the complete sensor, is installed into a vacuum isolated tube. So the green part and also the brown part is vacuum isolated, whereas the LNG is in the yellow part. And we have a LNG backwashed sensor element to optimize the heat distribution. So in this area, we've got also LNG in this side of the cap, so that also behind the sensor, we have lower temperatures and optimize the measurement with this. Then we are talking about mechanical strength and thermal expansion. So if you put a cylindrical structure like a thermal well into a external flow, there will a regular pattern of vortices will formate, and that's called the von Karman street. So depending on the frequency or the natural frequency of the thermal well and on the shedding frequency of the flow, the cylinder or the thermal well will start to vibrate and oscillate. Especially the thin and long structure of our thermal well that we have here is very susceptible to damage by vibration. And on the other hand, reducing these or to know about the stresses that are with our thermal well, a thermal well calculation according to ASME, PTC 19.3 or DIN 43772 should be made. So the thermal well, of course, does not follow the ASME regulations, so it's not possible to follow the rules one-to-one, but it's able with the DIN calculations. And on the other hand, of course, the thermal well will show thermal shrinking effect. So if we install it at 20 degree plus and then we cool it down to minus 160 degree, of course, it will get shorter, and we should not avoid this movement. Otherwise, we get additional stresses to the thermal well. So what do? So we reduce the free swinging length by a support structure. You can see that the support structure in here. So it's above the thermal well, above the insertion length. So the movement in X and Y direction is minimized, and we are able to guarantee the stability against the flow-induced vibrations. To compensate the thermal shrinking effect, the support structure allows free heat expansion. So movement in Z direction is still possible. And as I already said, the support structure is best backwashed with LNG to have also cooling effects on the backside of this complete support structure. Okay, so as a summary, temperature measurement in LNG metering needs to be accurate to determine the correct flow rate and also LNG compositions. These special applications require special temperature sensor designs. The Endress Hauser design I've just introduced to you has been qualified in the VSL flow calibration rig. And in the end, it's a perfect solution to measure temperature accurately in cryogenic applications. Yes, that's what I wanted to show to you. Are there any questions?
Of course there are. So no, great that you participate and that you participate actively. So I just put some of those questions on screen for you, Robert, and I will switch off my signal so that you see exactly what people ask and what people explain. So our stratification.
Okay, yeah, great. Yes, stratification is the multiple temperatures at different elevations within a LNG storage tank. Yes, okay. Sorry, I did not know this expression, but okay, this measurement is foreseen for pipes, and we do not have these stratifications inside of the pipe. So you have one flow of LNG in there, and it should have, of course, there might be temperature differences also, but here is a very small pipe, so the temperature distribution should be quite homogeneous.
But to add something to that, Robert.
Yes, of course.
We have temperature systems in place also for tank gauging solutions, where we have multiple measuring points in the tank itself to take care of the stratification, because it's a very important topic within the storage facilities. But like you said, not in a pipe. Yep.
Yeah, I do not know if the participant were able to hear it, so it was very hard for me. But maybe I shortly get this thought. So Rob said we are also offering temperature measurement in different elevations of a tank, so that we are able to measure the temperature distribution over the tank, and have also the solutions for storage measurement in temperature available. Thank you. Then must the sensor be positioned perpendicular to the flow directions? That depends on the application. It must not. Of course, you're also able to have it in the direction of the flow or against the flow. Then you have less effects of the vibrations of the water shedding. But on the other hand, it's maybe more difficult to install it. So here we had a very small pipe, and we wanted to, though the position of the sensors was more or less given. So, and here this was the best possibility to place the sensor. Of course, if you are able to place a long and thin sensor in this pipe, in the flow, you are also able to get very good measurement results. What do I mean by LNG backwash? Maybe we go back to, yes, this slide. So we've got the yellow pipe is the pipe of the LNG, and we've got some drillings in here that the LNG can also flow through this cap part of the thermal well, so that we have a cooling effect also from the backside of the sensor, and can achieve a better accuracy of the measurement and have lower heat transfer from the ambient to the sensor element. Yes, absolutely. There is the possibility to have a remote housing. Also makes sense. What we do, we have this cable sensor. You don't see it that good. But also we are using a remote housing here. So a remote field transmitter TMT 162, sorry. And it absolutely makes sense to get the electronics out of the area with the low temperatures, with icing effects, and so on. So we are able to install that also in remote position. The total accuracy of the temperature measurement is plus minus 0.5 Kelvin, which is for the application very good. So, but you also see that we have to take a lot of measures and have a very special sensor to achieve this accuracy. Recalibration frequency and model of the temperature sensor I showed. So the model of the temperature sensors, it's a PT1000 element. It's a thin film sensor. We have a MGO tube to generate this insert, and the recalibration frequency, that's a question that the user has to answer. So depending on the terms of conditions of the user, they have to recalibrate the sensor. From my experience, I would say that a PT1000 and at this low temperatures, there's very few processes, or the processes of degradation of the PT1000 are very slowly, so the recalibration should not be too often, but it's depending on the requirements of the user in the end. Okay, no more questions from the audience then. Thank you for participating. Thanks for your time, and hope to see you soon, and back to Rob.
Yes, well, thank you again, also Robert and Benjamin, for a great presentation, I think. I like to point out that a handout of this presentation is also available in the handout section of your screen as well. So please use that, download it, and multiply it to your colleagues that have some interest as well. Might you have more questions? Please do not hesitate to ask the question to robert.huth@endress.com. I mean, our email addresses are very simple. It's first name, last name with a dot in between @endress.com, or send it to me, rob.vermeulen@endress.com, and I will make sure that the experts can help you answer those questions. So thanks again very much for your presentation, Robert and Benjamin. I think it went great. Next week we have 2 new sessions, one on Tuesday and one on Thursday, same time, same location. Probably not in the same location as you, Robert, whether it's beautiful up there. But the topics will be still very interesting and applicable for the oil and gas industry. And with this, I like to give you the last word. Any last words, Robert?
Yeah, thank you. No, I'm done for today.
You're done for
yes,
today.
Thanks for participating. Thanks for the possibility to present this, and hope we'll have further interesting webinars and sessions in the future.
Definitely. Benjamin?
Yeah, if you liked it, tell others, share it. And as Rob already said, there are lots of more interesting topics. We try to reach you in times like these on different channels, and maybe a little bit different than just lecturing, but more in an interactive style. So therefore, take care. And what Rob said in the beginning, wash your hands frequently and stuff like that.
Definitely. And with this, I'd like to end the webinar. Thank you very much.
Thank you. Bye.